phase plant's generator section, where phase plant's sound begins, you can select and load an oscillator named analog. Analog meaning analogous in the way sound and electricity oscillate. This oscillator models the way analog synthesizers generate sound. When something is oscillating, it is vibrating or moving in a back and forth motion. Sound is created by oscillations in the air. Traditional analog synthesizers use electricity to create oscillations in order to create sound. With these classic analog instruments, the sound they create begins with an oscillating waveform generated by electricity. Digital instruments like phase plant can model this type of sound generation. When you first load phase plant's analog oscillator into the generator section, phase plant will automatically create a group with the analog oscillator and an output for its sound. This output for its sound has what is called an envelope. This envelope controls the amplitude of the sound being generated. In other words, this output's amplitude envelope controls the volume or loudness of this oscillator's sound over time. Each of these settings, attack, decay, sustain, and release, control a different stage and loudness over time. The sound of this oscillator will be routed through this envelope output. There is a selectable output option here in this drop-down menu, which is currently set to lane 1. If you delete this output, you will not hear the oscillator's sound. You can reload this output by selecting here in this blue rectangle when it gets highlighted and choose Envelope under Output. This puts it back in the group with the oscillator. Notice these gray arrows at the right side of this group. This indicates the signal path of the audio in this group. The sound goes from the oscillator to the envelope output, then to the effects lanes. With these lanes, you can insert effects after the audio signals that come from this generator section. With phase plant's analog oscillator, you have the choice of 4 different classic oscillating waveforms: a Sawtooth waveform, a square or pulse waveform, a triangle waveform, and a sine wave. What you hear in any sound is determined by air pressure changes. These waveform shapes represents how, with this instrument, we can change air pressure over time. In other words, these shapes represent how the pressure in the air molecules will repetitiously change over time from high to low pressure when sound happens. These waveforms graphically represent this change in air pressure over time. Graphically, high pressure is represented with an upward or positive change, and low pressure is represented with a downward or negative change. These changes repeat over time at a certain rate, or in other words, at a certain frequency. This repeating oscillation will generate sound. Once again, the shape of each of these waveforms is just a graphic representation of the way the air pressure will change over time in the sound from high to low pressure. In other words, each of these different waveforms will generate a different sound. You can select between the different waveforms here. This first one on the left, the Sawtooth waveform, will generate sound that contains integer harmonic frequencies. All sound is a combination of different frequencies happening at the same time. Harmonic frequencies have a harmonic relationship with each other. More on harmonics in a second. The rate any waveform oscillates determines its frequencies. Frequency is measured in hertz. Using a spectrum analyzer, you can measure the frequencies this waveform generates. Each peak in the window represents a different frequency in the sound. and the height of that peak represents the amplitude or loudness of that frequency. The frequencies a sawtooth wave generates are called harmonic frequencies. You can see that the amplitudes of these frequencies descend in loudness in a linear way. Harmonics are multiples of a fundamental frequency. To determine the harmonics of a frequency, we multiply a fundamental frequency by a number, 1 times, 2 times, 3 times the frequency, 4 times, and so on. I will speak on the details of harmonics a little later in this video when I cover this oscillator's tuning controls. Let's compare a sawtooth waveform's harmonics to the harmonics a square waveform will generate. With a square wave selected while playing a note, compared to the sawtooth wave, you will hear a different set of harmonic frequencies. A square wave will generate a sound that contains odd harmonics, that is, every other harmonic frequency. You can see the frequency content of this square waveform in Ableton's spectrum analyzer. Like the sawtooth waveform, these harmonics descend in loudness in a linear way. While playing a sound, if you select between the sawtooth and the square waveform, you can see in the spectrum analyzer that the square wave will generate half of the harmonics a sawtooth wave will generate, but the linear loudness change of the harmonic content is the same. When you have the square waveform selected, you will notice that this knob labeled PW on the right side of this oscillator's window is highlighted. If you select another waveform, this grays out. The pulse waveform is the only waveform with this oscillator that uses this control. PW stands for pulse width. A square waveform is a type of pulse wave. A pulse wave can oscillate, or we could say pulsate air pressure in one positive amount and one negative amount. A square waveform oscillates in 2 states, 50% positive and 50% negative, and pulses between both, indicated in the graphic in equal states like the sides of a square. If you adjust the pulse width control, you will see in the graphic this relationship change. The pulse width control sets the amount of time in each cycle of an oscillating pulse wave that it will spend in a positive versus negative state. The pulse width is set as a percentage. If you turn the knob to the right, it increases up to 100%, and then to the left down to 0%. When you increase the percentage amount, the line at the top of the graphic increases in length, while the line at the bottom decreases in length. When lowering the percentage, the opposite happens. The top decreases while the bottom increases. The line at the top of the pulse wave's graphic represents its positive pressure change, and the line at the bottom represents its negative pressure change. The length of the line represents the amount of time one cycle of an oscillation spends in either a positive state or a negative state. Different pulse widths create different sounds. If you listen while adjusting the pulse width percentage, you will hear the sound it generates changing. If you use a spectrum analyzer while doing this, you will see how the loudness of each harmonic changes as you make adjustments and how that relates to the sound you hear. You will also notice that if you set the width to 0% or to 100%, you will see in the graphic just a line, and there will be no sound. The line indicates that there is no oscillation because it is staying in a neutral state. With no oscillation of air pressure, there is no sound. The next type of waveform you can choose is the triangle wave. If you select the triangle-shaped waveform graphic and listen to the sound while analyzing its harmonic content, you will hear and see the same odd harmonics that a square wave generates. The only difference in the sound is there are less harmonics in a triangle wave versus a square wave. Specifically, there are fewer higher harmonics in the sound of a triangle wave versus the harmonics in the sound of a square wave. You can see in the spectrum analyzer that the loudness of each harmonic in a triangle wave decreases in loudness exponentially versus the square wave's harmonics, which decrease linearly. Listening to the sound of a triangle wave versus the sound of a square wave, you might say a triangle wave sounds like a muted square waveform. The last oscillating waveform that you can choose with this oscillator is the sine wave. A perfectly smooth circular oscillating sine wave will generate one single frequency. If you analyze the sound in a spectrum analyzer, you will see just one peak. Where this peak is showing in the spectrum window is the frequency of this waveform. It is the frequency this waveform is oscillating at. That is how many times in 1 second it is oscillating, which also relates to the pitch or musical note it will sound. You can see in a spectrum analyzer as the frequency increases, the pitch becomes higher, and as the frequency decreases, the pitch becomes lower. The frequency the oscillator is generating is determined by the incoming MIDI. I am currently using a MIDI keyboard to send faceplant pitch information. You can adjust the tuning of the incoming pitch or frequency with these controls here. Semitones change the sounding frequency by divisions of half steps in chromatic scales. Semitones and half steps are the same divisions. Semitones or half steps are the notes on a keyboard. If you increase the value of the semitones, the pitch will become higher in increments of semitones. If you decrease the amount, it will lower by increments of semitones. If you increase the amount by 12 semitones, the note will be 1 octave higher than the incoming MIDI note, the note you are playing on the keyboard. If you decrease the amount by 12 semitones, the note will be 1 octave lower. The decimal points to the right of the semitones are cents. You can fine-tune a semitone by cents. There are 100 cents in a semitone. As well as the semitone control, you can change the incoming frequency by once again what are called harmonics. Harmonics are multiples of a fundamental frequency. The fundamental frequency is determined by the incoming MIDI note. Once again, I'm using a MIDI keyboard. These numbers of the harmonic settings indicate what you are multiplying the incoming frequency or note by. With the harmonic tuning settings, with 1 times the frequency of the oscillator, it will have the frequency of the incoming note you are playing. 1 times whatever note is playing is the same note. Every note has a specific frequency. Setting the harmonics to 2 times multiplies the incoming frequency of the note by 2. We measure frequency in hertz. If you play a G note with a frequency of 100 hertz and have the harmonic settings at 2 times the frequency, it will sound at 200 hertz. If you play the same G note with the harmonic setting at 3 times the frequency, it will generate 300 hertz, then 4 times, 5 times, 6 times, and so on. These multiple numbers, 200, 300, 400, 500, and so on, are the harmonic frequencies of a G note played at 100 hertz. Different notes will generate different harmonics. Depending on the frequency of the fundamental note will determine the frequency of the harmonics. As described with different wave shapes for sound generation, using the sawtooth, square, and triangle waves, these wave shapes generate harmonic frequencies. For instance, a sawtooth wave played with a G note at 100 Hz will also generate the harmonic frequencies, 200, 300, 400, and so on, all of them sounding at the same time at decreasing amplitudes. The shift tuning control settings can fine-tune faceplant's incoming frequency. The shift settings adjust the oscillating frequency at finer fixed increments. This is a setting you can adjust for fine-tuning the generated frequency. To the left of the frequency tuning controls, you will see the level control. Level sets the amplitude of the oscillating waveform. Level is set with a percentage. If you increase the amount, you will see in the graphic the height of the waveform increasing in size, and you will hear the loudness of the sounding waveform increasing as well. If you decrease the level setting, you will see the graphic of the waveform's height decrease in size, and you will hear the loudness become quieter. The height of the waveform in the graphic represents how much pressure is happening in the air. How we perceive loudness or volume relates to the amount of pressure the sound waves are exerting in the air. The more pressure in the air, the louder we perceive the sound, and less pressure we perceive more quietly. You can also adjust the loudness of the generated sound at the output of the audio signal with this knob called gain. Gain sets the loudness level at the output before the signal passes to the effects lane. With audio signals in general, it is not uncommon that the level of your signal can be changed and set at different parts of the signal path. The panning control at the output will send the signal to either your left speaker or your right speaker. This is how stereo works. With stereo, you will have two audio channels, a left and a right channel, whose signals are sent to the left and to the right speaker. Panning places the sound within the stereo field from the left to the right. With panning set all the way to the left, you will only hear sound out of your left speaker. With panning set all the way to the right, you will only hear sound out of your right speaker. If you are using headphones, you will only hear it to the speaker for your left ear or only to the speaker for your right ear. Panning in between sets a level of volume at a percentage to either speaker. As far as the analog oscillator signal is concerned, it is a mono signal, meaning it only has one audio path. When you send your audio signal from the oscillator to the envelope output via the group, the output is split into a left and a right signal. This is what connects the sound of the oscillator to an output for its sound, and ultimately that sound to your speakers, or headphone speakers. Once again, without this envelope output, you will hear no sound. The farthest oscillator control, to the right of the tuning controls, is this oscillator's phase setting. Phase is an important but often not intuitive part of sound and audio. If you don't understand how phase is important to audio and sound, you may also wish to watch the video on sound characteristics. An oscillating waveform's phase becomes a consideration in sound when it relates to another oscillating waveform. Sound is complex with many different parts of a sound happening together at the same time, meaning lots of different frequencies happening at the same time. This is why phase must be considered when you are creating and designing sounds. Phase is measured in degrees like a circle. An oscillation of a waveform is like a circle. Sound starts from a static position, then moves to a higher pressure position, then to a lower pressure position, and back and forth in a circular motion. The point a waveform is at in its cycle is what phase measures. When you change the phase setting, you will see the waveform graphic shifting from left or to the right, depending on how you are setting the phase. At the left edge of the window, this indicates what position the waveform will start oscillating from. Approximately in the middle of the window's edge, right here, is where 0 degrees is at. 0 degrees is the start of a waveform's phase, and when set to 0 degrees, the waveform starts oscillating from here. If you select a sine wave, you will see on the left edge of the window where 0 degrees is at in this waveform. This is where this sine wave cycle will begin. If you increase the phase to 90 degrees, you will see that the graphic has shifted position and now indicates that the sine waveform will start at its highest pressure point in its cycle, which is 90 degrees. If you adjust the phase after 90 degrees in the graphic, we can see the line's movement moves downward towards the negative or lower pressure points. If you set the phase to 180 degrees, you can see on the left edge of the window, the waveform is halfway through one cycle and is back to the position where 0 degrees was. The difference between 0 degrees and 180 degrees is that at 180, the waveform starts moving towards the negative or low pressure side of the cycle, indicated graphically moving downward. Versus at 0 degrees, it starts by moving towards the positive direction, graphically moving upward. Phase plant measures one cycle of its oscillator phase with a positive and a negative 180 degree setting, measuring 180 degrees positive and 180 degrees negative. Combined, this is 360 degrees for one complete cycle, like a circle. While paying attention to the position of the waveform's line at the left edge of the window, relative to 0 degrees, which is in the middle of the left edge, if you change the phase through all the degrees, you will see the sine wave's graphics movement as a circular movement. The positive 180 degrees of the circle is the top of the circle, and the negative 180 degrees is the bottom of the circle. While sounding a note, notice that no matter where you set the phase of the sine wave, when oscillating, it sounds the same. We don't hear phase. The way it could affect the sound is how it relates to other waveforms. One way phase becomes important to the sound is its relationship to another sound. A general rule of thumb about phase is that when two waveforms are in phase, meaning they are moving together in the same positive and negative pressure movements, the sound becomes louder. And when two waveforms are out of phase, meaning one waveform is moving positive while the other is moving negative, we hear a decrease in loudness. Using phase plant, one easy phase test you can try with this oscillator is to load another oscillator into the group. You can do this by hovering the cursor in the group, and when this dashed blue line appears, select and load another analog oscillator. Set the waveform of this oscillator to also be a sine wave. Now, if you play a note and switch on and off the added oscillator, by selecting on and off with this blue square at the left corner of the oscillator, you will hear the sound becoming louder when on and quieter when off. That is because these waveforms are in phase. Now, if you change one of the oscillator's phase settings to 180 degrees and play a note, what you will hear is silence, because both these oscillators are set 180 degrees out of phase from each other. If you change the phase to different degrees while sounding a note, you will hear the loudness increase and decrease depending on the oscillator's phase relationship. This is at the heart of why phase is important to sound. Once you develop a skill set in sound design with synthesizers, you will find that phase is a great tool to use for shaping sounds. This is why we have the option for setting phase in synthesizers. Phase plant's analog oscillators have this option. Another option phase plant's analog oscillators have for shaping a sound is oscillator sync. Above the pulse width control knob, you will see a sync knob. When you adjust this control, you will hear the sound changing. You will also see the waveform graphic changing in the window when you do this. As you increase the sync amount, you will hear higher and higher frequencies and harmonics entering the sound. This can become very harsh to the ears quickly. You may want to turn your speaker volume or headphone volume down when you try this. What is happening here is the sounding waveform is syncing to another cycle of a waveform. In other words, another frequency. What frequency or cycle the sounding waveform is syncing to is determined by the sync control knob. The cycle the oscillator will sync to is set by multiplying a number by the sounding wave's frequency. What this means is that at different sync settings, every time the syncing oscillator's waveform cycle starts over, it causes the sounding oscillator's cycle to start over. You can see in the graphic where the waveform is starting over from. This causes a new shape for the sounding waveform, which creates a new sound with different frequencies. You can see and hear at certain points the cycles line up and you hear a higher pitched frequency. Oscillator sync is a classic, common way to shape sound in analog synthesizers. A way you can use sync or any other controls on this oscillator to shape the sound over time is by modulating that particular control. That is, by modulating the setting of that control. You can change a setting or a control over time by using modulation. The section of phase plant at the bottom of its window is the modulator section. Modulators have the potential to change a parameter of the synthesizer's sound. For example, oscillator sync in the analog oscillator. The output for the group has an envelope that controls the loudness of the sound. This is an example of an envelope modulating amplitude. If you select in the modulating window at the bottom, you will see a drop-down menu of potential modulators for this synthesizer. Envelopes and LFOs are common modulators in analog synthesizers. If you select an envelope as a modulator, you can use this envelope signal to modulate another part of this sound, for example, oscillator sync in the analog oscillator. When you select the orange plus sign at the output of the envelope, you will see many other plus signs appear all over the synth. These are all the possible destinations we can modulate with this envelope. If you hover the cursor over the plus sign under oscillator sync, you will see a virtual signal path appear as a dashed orange line. You will also see a small pie graph, a little circle under oscillator sync. If you click on that and hold and drag, the pie graph will indicate how much that signal will modulate the sync control. If you make adjustments with this and the envelope settings, you can shape the sound in many ways using oscillator sync. This same idea applies to all other parts of the synthesizer. For example, the tuning controls and pulse width. This idea is just a microcosm for all the ways and parts of this synthesizer that can control and shape sound, and the ways those parts can be controlled and shaped with modulation. For more on modulation, see later videos. The last function of this oscillator is called Unison. You can turn Unison on and off by selecting the blue square in the upper right corner, called Unison. When you select Unison, you will see a new set of controls appear in the window of the oscillator. An old-school sound design technique using analog oscillators is to use two oscillators sounding at the same time, then you detune them from each other. This causes a different phase relationship with the frequencies in the sound, the two sounding oscillators. This creates a pleasingly thicker sound, similar to a chorus effect. You can try this by loading a group with two analog oscillators. Try this at first by selecting Sawtooth waveforms for both. Then use the shift control to slightly detune one of them from the other. Listen to how this sounds as you do this. This is what Unison is. What Unison does is it adds other voices, in other words, other oscillators that you can't see but you can hear, while having the option to detune them from each other in different ways. Phase Plant's Unison defaults to 4 voices, but you can select up to 8 voices here. With 4 voices selected, and you adjust the detuning control, the 4 voices will detune from each other. The more you detune them, the more the voices spread apart from each other. The more the frequencies of the voices spread apart from each other. Phase Plant's Unison has a number of different ways to tune and detune each voice from each other, including creating chords. See later videos for the details of all these modes. Just playing around with some of these different modes, you will easily find great sounds. This is a great part of Phase Plant's Unison that other synths don't always have. One of the controls that is available when Unison is selected is spread. The spread control sets a stereo field for the different Unison voices by panning them from left and right, by spreading them apart in the stereo field. Another control that appears when Unison is on is blend. With the blend knob, you can make adjustments to the level between the side and the middle Unison voices. With Unison on, another control that appears is a multi-knob, and depending on the Unison mode you have selected, you will see the farthest knob on the right has different control settings. When using different Unison modes, for example, you may see bias, balance, range, and center. These control different elements of whatever Unison mode you have selected. I will cover the details in all of these options and modes in a later video.